So the Wii U Gamepad was basically a tiny computer. It connected to the console with Wi-Fi, it used the same video codec as Blu-rays and YouTube. In theory, reproducing it should have been easy, except for the tiny obfuscation Nintendo made to the Wi-Fi protocol. An obfuscation that you'd think would be dead simple to bypass, but has instead taken me years to fully get around. So when we last left off, I'd managed to put together a pretty viable re-implementation of the Wii U Gamepad, which I'd given the name Vanilla. It was based on code from a 10-year-old proof of concept called DRC Sim, developed by MimaHacks and later Rolando Islas, and much like DRC Sim, Vanilla primarily ran on Linux, since Linux is one of the very few major operating systems that gives you enough control to do Nintendo's obfuscated Wi-Fi handshake. But desktop or even laptop Linux doesn't exactly make for a great Wii U Gamepad replacement. For this to have any real future, we were gonna have to port it over to something that could actually take the form of a handheld game controller. And as I started exploring the options, well, I started to understand why DRC Sim had largely remained a proof of concept. For starters, it became pretty clear early on that not all Wi-Fi adapters were built the same. Many of them seemed to work, but some of them inexplicably didn't. DRC Sim, for their part, recommended only one Wi-Fi chipset, the Raylink RT2800, famous for being one of the most Linux-friendly Wi-Fi chipsets around. I was a little more ambitious. I wanted to support as many as I could, and open up an official channel where users could test hardware and report its compatibility. As I pulled information from users, two patterns quickly emerged. Chipsets from Realtek generally didn't work. Chipsets from Broadcom generally didn't work. I didn't know why, but the evidence was clear, and also pretty annoying. These are two of the most common Wi-Fi vendors in the world. Even if you never pay close attention to them, you've probably still heard their names before. Realtek is the go-to vendor for USB Wi-Fi adapters. Literally, if you take the top 10 Amazon search results, Realtek comprises every single one. Meanwhile, Broadcom is the go-to Wi-Fi vendor for portable devices. Phones, tablets, laptops, Raspberry Pis, even the Nintendo Switch. In essence, a lot of platforms that would make pretty good Wii U gamepads. Suffice it to say, it would be very helpful if I could get both of these to work. But at this point, that was a very big if. I decided to tackle Realtek first, since I'd already bought a really compact Realtek-based Wi-Fi adapter, specifically in the hopes that it would come in handy for this. Right off the bat, these Realtek chipsets are unusual for Linux because they require installing a driver. For the most part, Linux users don't really need to install drivers because an absolutely massive amount of them are built directly into the kernel. I mean, you'd have to be using something pretty obscure for it to not be supported by the kernel, such as the most popular Wi-Fi chipset in the world right now. And it's not like the driver is some random community project either. It was made by Realtek themselves. How in the last several years has it never made it into the kernel? Well, no matter, let's go ahead and test it out. The Realtek adapter fails early. When trying to sync with Wii U, we get a cryptic control event assoc reject error. Presumably it's doing something to make the Wii U reject it. It's okay, buddy, we've all been there. Well, I figured that driver we had to install was our first lead, so I started digging through its source code to see what might be going wrong. But I soon discovered there wasn't just one driver for these adapters. Many forks existed from people dissatisfied with Realtek's weak Linux support, including one from Rolando Islas, one of DRC Sim's primary maintainers, in an apparent attempt to get it working with the Wii U. Does it work? I don't know. It only compiles on versions of Linux that are over 10 years old, and even then it's not compatible with any adapters I own. I tried to port its patches over to a newer driver that is, but it didn't seem to make a difference. I don't know if I got something wrong or if it never worked in the first place. Rolando doesn't really say whether it actually works or not. Clearly I would need to investigate more, except for the fact that I didn't. One of those Realtek drivers was not like the others. It wasn't a fork of Realtek's existing code, it was completely new code written from scratch. I mean, sure, if it's not officially supported, I guess anything goes. Well, it turns out that completely new driver is part of Wireless Next, a branch of the Linux kernel where new drivers are developed and tested before they're eventually merged into the mainline kernel. GitHub user LWFinger maintains a backport of the driver so you can use them on current versions of Linux. And remarkably, this driver works perfectly with vanilla. So apparently Realtek just wrote their driver so incorrectly that not only did the kernel devs feel the need to completely write a new one from scratch, it also just broke vanilla somehow. But honestly, this was a huge relief. These extremely common adapters were indeed compatible. You just had to install the right driver. So that really just leaves Broadcom. Could we be so lucky that it's just a driver issue again? Well, at first glance, it seems promising. Unlike the Realtek adapter, it does actually sync. But when it comes time to connect, it throws that same ASOC reject error. You might guess it's the same root cause, however, this time the driver is already part of the kernel, and presumably passed whatever standards the Realtek driver didn't. Still, I sifted through it to see if I could figure out what was wrong. But it became clear pretty quickly that this driver didn't block vanilla. In fact, it didn't really do much at all. Okay, so there are basically two types of Wi-Fi adapter. The first type is just a dumb radio. All it does is convert between bits and airwaves, nothing more, nothing less. As far as the Wi-Fi protocol stuff, like performing security handshakes, parsing incoming data, and formatting outgoing data correctly, all of that is done in software on your computer's CPU, usually by something like WPA Supplicant, which is what we use with vanilla. Linux refers to these as soft Mac devices, and they're the cheapest, easiest, and therefore most common way to design a Wi-Fi adapter.
I read in rap pages, they referred to me as soft. Yeah, more like soft Mac.
But the second type isn't a dumb radio at all. No, these have their own CPU, their own memory, their own firmware. Basically, they're a whole separate system on a chip that can do all of that Wi-Fi protocol stuff on its own. Linux refers to these as full Mac adapters, meaning we narrowly avoided this being very funny. Full Mac adapters are significantly more complex than their soft Mac counterparts, but that complexity does have its benefits. If you're designing a small, low-powered portable device, offloading all of that processing to a dedicated chip can save you valuable CPU cycles and battery power. But for us, it's a big problem because if the chip is handling the whole authentication handshake itself, then there's no way for us to modify it to be compatible with the Wii U. The process is effectively baked into the chip. Even assuming there's a way to acquire the chip's code, modify it, and send it back, that still means wading hip-deep through a completely undocumented blob of binary code. Yeah, if you think any of these companies open source any of their shit, prepare to be severely, severely disappointed. What, do you think we could just share our trade secrets with everyone? The trade secrets that implement a completely open standard? Even if we were to successfully do this for one chip, there are hundreds of full Mac chips out there. It very quickly becomes impractical to get every single one working. The only reason those Realtek adapters were immune is because they had effectively done it backwards. They made soft Mac hardware, but for some reason wrote a full Mac style driver with its own self-contained implementation of the Wi-Fi standard. Yeah, they literally wrote the driver wrong, which is why it could be immediately fixed by a better one. No wonder it never made it into the kernel itself. But Broadcom is a seasoned veteran of full Mac chips. That's essentially all they do nowadays, making them a near impenetrable wall for the Wii U. So yeah, keep that in mind as we start to port vanilla to other platforms. Depending on the Wi-Fi hardware involved, it may be impractical or even impossible to get it to connect to a Wii U. When it comes to making a device that's more Wii U Gamepad shaped, several potential solutions come to mind. And when I polled my viewers asking which one they wanted to see me tackle first, the winner was none other than the Raspberry Pi. On paper, the Pi makes a lot of sense. It runs Linux, which we're already using, and even the lowest end, cheapest one, the Raspberry Pi Zero, theoretically has everything we need, including 802.11n Wi-Fi on the W variant, and a solid ecosystem of sensors, displays, webcams, and more. In theory, you could build a gamepad out of this. The only concern on paper is, well, take a look at whose name is on that Wi-Fi chip. Yeah. But even if it wasn't Broadcom, it's also only 2.4 GHz, while if you remember, the gamepad only operates on 5, so either way, the onboard Wi-Fi is useless to us. But the nice thing about a device that runs Linux is we can just plug in a compatible softmac USB Wi-Fi adapter and use that instead, so while a little inconvenient, it's far from a deal breaker. But I did also look at other single board computers just to see what was available. The Orange Pi 03 and 2W, which are ironically colored blue, were particularly strong contenders since they were some of the very few that provided 5 GHz Wi-Fi and a cute little antenna as standard. Unfortunately, when I bought one to test it out, I quickly realized it was yet another full Mac Wi-Fi chip, giving us that all too familiar ASOC reject error. If we were going to have to use a USB Wi-Fi adapter anyway, I figured it made the most sense to stick to the more tried and true options. So I promptly stuffed the Orange Pi into a drawer and refocused my attention on the Raspberry Pi. The main challenge with the Raspberry Pi would be getting Vanilla to work well on such modest hardware. Out of the box, it runs like this. Yeah, not exactly a seamless gameplay experience. To be fair, I decided to target the original Pi Zero from 2015, which is quite slow. I mean, it's 10-year-old hardware the size of my thumb, what do you expect? But I chose it because it felt like a really good baseline. Even though there's way faster stuff available today, I figured if I could get it to work on there, I could get it to work on anything. But to do it, I was going to need to strip everything back. No Qt interface, no desktop environment, no window manager. We're drawing straight to the GPU with as little overhead as possible. I ended up live streaming this process, which some of you may remember. If you've ever wondered what it's like to code with 1,000 people looking over your shoulder, well, I'm now intimately familiar with the feeling. But it was fun, and if you want to watch through the VODs, I'll leave a link to a playlist in the description. Over the course of 15 days, I pushed the Pi Zero as hard as I could, starting with writing a whole new front end in STL, which is a much lower level library than Qt, giving you nothing but the most basic drawing functions out of the box. Cool, but that's exactly the kind of fidelity I wanted. Like I said, I didn't want anything running that didn't need to be. Crucially, STL provides a path to draw straight to the GPU using a Linux kernel feature called KMS-DRM. Yes, I know it's a hilarious acronym, but it actually stands for Kernel Mode Setting Direct Rendering Manager, which is a long way of saying we can send stuff straight to the GPU. So that wasn't too hard, but remember, we're not actually just drawing a white rectangle going across the screen. What we really need is to display decoded video frames from the Wii U. And unfortunately, as we saw, even the gamepad's pitiful 480p is way too much for the Pi Zero CPU to decode in real time. Thankfully, the Pi Zero has a separate hardware decoder chip capable of decoding up to 1080p 30, more than enough for our purposes. But if we really want this to run smoothly, and we do, we want those hardware decoded frames to go straight to the GPU without having to make any kind of round trip back to the CPU. And this makes things surprisingly complicated. While the Raspberry Pi fully supports doing this, if there is any official documentation about how to do it, I haven't seen it. All I did find was a sample project on GitHub that I heavily used as a reference. And if you want to use the legendary FFmpeg library for decoding, which I did to make my life just a little bit easier, you have to use a fork made by the same guy because even it can't do this out of the box. I'm almost surprised anyone can decode video with this thing. But after several days of figuring this out, the video feed finally came through. Yeah, look at that! It's a Raspberry Pi being a gamepad. Funnily enough, when you output directly to the GPU, it just kind of draws over whatever was on there before. But that's fine, it just means we're operating at a very low level, which is what we wanted. And for such a slow device under normal circumstances, it was kind of amazing how smooth the video feed was. Yeah, everything you're seeing here, except for my face, is running on the Raspberry Pi Zero, a $5 computer from 2015. But it definitely wasn't perfect. The modest performance was indeed an issue. It frequently stuttered or completely skipped frames, occasionally leading to a slightly corrupted picture. But even worse, there was an enormous amount of delay. We're talking like nearly half a second, which is enough to make games effectively unplayable. This was bizarre because on PC there was no delay at all. If this was a limitation of the Pi itself, that effectively made it a non-starter for running vanilla. Well, once again, there was virtually no documentation about this. Nothing that said, oh, by the way, this thing has like half a second of video delay, even though you'd think that would be really important information to share. What I did find was an obscure forum thread from 2013, where someone seemed to be describing exactly what I was talking about. They too encountered latency between roughly half a second to even multiple seconds, and ironically one of the replies even mentions the Wii U Gamepad while speculating how to achieve a zero latency video feed. And while many dismissed the question entirely, saying all decoders have some amount of delay, the OP eventually figured out that if he tweaked one of H.264's SPS parameters, he was able to get rid of any perceptible delay. Okay, so I just threw out a bunch of acronyms that probably mean nothing to you. H.264 is one of the biggest video compression algorithms in the world. It's used in Blu-rays, a lot of web video, and of course, the Wii U Gamepad. SPS, or Sequence Parameter Set, is a major component embedded into all H.264 video streams, which essentially stores exactly how it was encoded, and more importantly, how to decode it. There are a lot of different options in here, but the crucial one for us is called Max Dec Frame Buffering. As you might guess, this tells the decoder how many frames it should buffer. Currently, we don't provide this option at all. Many parts of the SPS are indeed optional, in which case the decoder uses its best judgment. Evidently, by default, FFmpeg's software decoder on PC chooses not to buffer any frames, while the Raspberry Pi decoder does. But what's even the point of buffering frames in the first place? Well, one of H.264's defining characteristics is its use of temporal compression. Instead of storing every frame in its entirety, it saves an enormous amount of space by primarily just storing the differences between this frame and the last. In fact, it's possible to be even more efficient by having frames that reference both previous frames and upcoming frames. These are so-called bidirectional frames, and while they do help a lot with compression, they also by definition add latency because the decoder can't decode this frame until it receives the next ones. Naturally, to achieve low latency, the Wii U doesn't use these, but out of, I guess, an abundance of caution, the Pi decoder adds a bunch of delay anyway, just in case. Unless we specifically tell it doesn't need to do that with that max-dec frame buffering flag. This seemed like my best lead, so I set out to try modifying the SPS parameters. Unfortunately, this was a lot easier said than done. The Wii U never actually sends SPS parameters. Since the video feed is always the same, Nintendo correctly figured they could just hardcode them into the gamepad. But that means to get any off-the-shelf H.264 decoder to work, we have to, make some up. Now, so far, I'd just stolen mine straight from DRC Sim, and you might think it would be relatively simple to just change one of the parameters, but nope. These things aren't stored in a conventional way. They're actually compressed using an encoding called exp-glomb to pack the bits as tightly as possible. What this means is there's no easy way to even know where the parameter we want to change is without writing a full parser for the whole thing. I ended up deciding it would be easier for Vanilla to just generate its SPS parameters on the fly. After all, what if there are more parameters we need to change later? But this decision meant pretty much an entire day of figuring out the encoding, figuring out what each parameter did, working around byte endianness. It was the single hardest day of those Raspberry Pi streams, and the whole time I still didn't actually know whether it would solve the problem or not. Thankfully, it did. No way! No way! That is significantly better! Yes, that half second of latency was finally gone. But was it latency free? No. There was still a pesky 4 frames of delay, a lot better than before, but still just noticeable during gameplay. But after that day, I needed a break. I decided to focus instead on the other issue, the slow performance. I had a feeling with some optimization, Vanilla could run well even on the lowly Pi Zero. This was a lot more fun. There are plenty of simple tools out there that can tell you exactly where the slow parts of your program are, at which point all you have to do is figure out how to do that stuff faster. Ironically, the Pi Zero is so primitive that the tools don't actually run on it. Oh, interesting. So I just tested on my main PC, figuring slow code was slow code no matter what we were running on. The first big win came from the packet processing, another thing I'd taken from DRC Sim. The packets sent by the Wii U have headers with reversed bits. I don't know why, they just do. In order to read any of it, we need to unreverse those bits, or re-reverse them? But this only applies to the header. The actual data payload isn't reversed at all, making it odd that DRC Sim, and by extension Vanilla, would bit reverse the entire packet just to unreverse the data section later on. Now, reversing bits is an expensive operation, at least on x86. There's no dedicated instruction to do it, so we have to do it by hand. While ARM, the CPU family used on the Raspberry Pi, did introduce a dedicated bit reversing instruction later on, the Raspberry Pi Zero is too old to have it. So on both setups, this was an incredibly time-consuming operation. Not to mention, we were doing it twice. On the Pi, this amounted to several milliseconds per frame, which may not sound like much, but remember, a 60 FPS frame is only 16 milliseconds. No wonder it would struggle sometimes. So I limited the bit reversing, not just to the header, but to specifically only the fields we actually read, skipping over 99% of the processing it was doing here. There are also different methods of reversing bits, some of which are faster than others. My chat and I tested a few different methods and found a clear winner that was several times faster than the manual approach from DRC Sim, bringing the bit reversing on the Pi to sub 1 millisecond. The definition of working smarter, not harder. The next big slow point, I have to admit, was all me. I thought it would be cool to send Linux's actual battery state to the Wii U, so if your device's battery was low, the Wii U would tell you. Just a nice little aesthetic thing to make it feel more authentic. I figured we don't need to pull the battery state every frame, so I limited it to just once every 2 seconds. And it turned out this was a good impulse, because more recent STL3 documentation has stated retrieving power supply details may be expensive. Only problem is, my limiter contained a fatal bug that meant it did absolutely nothing, and vanilla would end up pulling the battery state every single frame anyway. Something that should have been completely inconsequential was hammering the CPU, which was particularly embarrassing since neither my PC nor the Raspberry Pi were even running off a battery. It's a fairly boring mistake, so I won't go into it. If you know programming, you'll be able to spot it from this screenshot. By the time I figured out this was a slow point, it was months later, at which point I'd completely forgotten that I'd even tried to write a limiter, and ended up writing a second one in another part of the code. And only while putting this video together did I realize I had done that. Well, at least the power state retrieval was finally limited properly, but I have gone ahead and removed the broken one so we aren't being redundant. Goodbye to yet another wasteful chunk of CPU time. I was also able to save quite a bit of processing by reworking the pipe. If you remember from episode 1, vanilla is split into 2 parts. The front end, which does all of the work of emulating the gamepad, and the pipe, which makes the connection to the Wii U and relays packets between it and the front end. There are a lot of benefits to this. It means only the part of vanilla that absolutely needs to run with root permissions does, and it means you can put the pipe into a virtual machine or another computer entirely to use a front end that can't otherwise connect on its own. However, if you really think about it, relaying between the pipe and front end on the same machine really just wastes time copying data around for no particular reason, apart from the fact that it was easier to code it that way. And this became especially clear on the lowly Pi Zero. Ultimately, even though it made the code a little more complicated, the right move was to optimize this, not just for the Pi Zero, but any platform running vanilla. Now, if you're running vanilla on a single machine, the pipe will still set up the connection as usual, but the packets will be received directly by the front end, bypassing the pipe entirely. No more copying data around for no reason. But probably the biggest, dumbest improvement was this. While connected to the Wii U, the pipe has a central loop to detect if the connection has dropped for whatever reason. To do so, it called a WPA supplicant function called WPA control receive. I was under the impression this function was a blocking function, meaning if there was no message to receive, it would just wait until there was. That is commonly how functions called receive behave, and even Google's AI overview will claim that it is. But it isn't. And by spamming calls to this function in a while loop, we're basically maxing out an entire CPU thread, which on the Pi Zero is a big deal. Since Wi-Fi disconnects are not something that need millisecond response times, I changed it to only check once every second, which honestly still might be more than strictly necessary, but is slow enough to make this check completely negligible processing-wise. With the main code optimized and running faster and lighter than ever, all that was left was building some kind of menu system. Remember, I started a whole new front end for this port, and for development, I'd just been writing straight terminal commands, but obviously that wasn't going to work for most people. Well, the most likely thing anyone was going to do with vanilla on the Raspberry Pi was make a dedicated gamepad clone. So we really wanted a menu system that would work on that sort of device. Something that was easy to use on a small touchscreen. Perhaps even something that fit into the existing Wii U aesthetic. And as I thought about it, it dawned on me that this kind of UI wouldn't just benefit the Raspberry Pi, it would benefit any platform that made sense to run vanilla on. Again, anything centered around a small touchscreen. I had originally planned to write different front ends for each platform, wanting to take advantage of each one's strengths and weaknesses. But I also realized it would be a huge pain making sure each one had all of the same features, and that if we instead had one front end that worked for everything, it would not only be a lot easier for me, but also sidestep that problem entirely. And with that, I made the difficult decision to discontinue the original Qt interface I wrote. While I like native desktop controls as much as the next nerd, as I've said in the past, desktop PCs are really the least sensible platform for a Wii U gamepad. It just doesn't make sense to continue maintaining a whole separate front end for it. Since STL already supports pretty much every major platform today, it was just a matter of putting together a UI. And after about a month, we had exactly that. This is now the main vanilla front end, designed from the ground up for small touchscreens, just like all Wii U gamepad games are. I'm aware it could look a little prettier and more Wii U-like, but the important thing is it works, and we can always refine it later. All of that optimization may have made vanilla run smoother on the Raspberry Pi, but there's one critical thing it didn't do. It didn't solve the 4 frames of video latency. On the one hand, it's only 4 frames. It's still playable, and you could probably get used to it. On the other hand, the point of this whole project is not to make something clearly worse than the gamepad, it's to eliminate the need for one. So the gameplay experience has to be just as good. I came back to the latency issue several times over the next several months, but I just never found a solution. My only conclusion is it's just how the Pi0's decoder is. It may have been good enough for the OP of that thread, but it's not really good enough to replace a real Wii U Gamepad. You may be wondering, what about the Pi0 2? Released 7 years later in 2022, it is significantly faster yet retains the same small form factor, as in, it looks pretty much identical. And today it even costs the same as the original Pi0, so there's no real reason not to use it. And surely it works a little better for this sort of thing. And it does. The occasional lag spots we encountered are pretty much eliminated on the Pi0 2, but the onboard Wi-Fi chip is still only 2.4 GHz, and fatally, its decoder still has those 4 frames of latency despite all those years of technical advancement. Just to be 100% sure, I wrote a tiny test program that does nothing but send and receive frames from the decoder and report how much they're delayed by. I then generated what should be an absolute zero latency H.264 video file and tried it out. And this pretty much precisely shows us the problem. We have to send 3 frames before the decoder sends anything back, and the feed remains 3 frames behind forever. Add another frame for VSync, which is enforced by the Pi's decoder to display pipeline, and that explains our 4 frames of latency. To me, this is conclusive. The least amount of latency we can even hope to achieve on the Raspberry Pi Zero is 4 frames. It is what it is. Well, there is one more thing to test. As we've established, FFmpeg's software decoder has no latency. And while it was way too slow for the Pi Zero 1, could the Pi Zero 2 be powerful enough to tank it? Well, it definitely can handle it better than the Pi Zero 1, and indeed, this does seem to eliminate the latency. But even with a quad-core, the CPU just isn't quite fast enough to keep up, resulting in this incredibly trippy video corruption. It's like if Mario Kart was developed by Jeff Minter. So after all of that, I can only conclude that the Raspberry Pi Zero, neither of them are really a suitable gamepad replacement. They can do it, but it's just always going to be a noticeably worse experience. The fact is, these are extremely cheap computers, and compromises must be made to pull that off. While it was frustrating to be so close yet so far, I did actually enjoy my time coding on the Raspberry Pi Zero. It forced me to scrutinize the code in a way I wouldn't have otherwise. Without it, I may never have found those maxed out CPU threads, which on my main PC amounted to a single-digit percentage of CPU usage. But vanilla is objectively a better program now that I have. Optimizing code for modest hardware really is a lost art these days, and it was nice to have a good reason to do that, even if it didn't quite end how we wanted it to. But that begs the question, what can we do? Obviously there are other single-board computers out there, but what are the chances they too have an undocumented decoder delay? Literally the only way to know is to buy one, spend the time figuring out how to use its decoder, and only then would I know if I'd wasted all that time and money or not. Well, remember the Orange Pi I mentioned earlier? It too has no documentation about how laggy its decoder is, but I figured it would be worth testing just because I had one sitting around. I reworked my test program to the Orange Pi's decoder and what's this? It sends back frames immediately? It doesn't forcibly delay us by some arbitrary amount? Could it be true? Do miracles really happen? Bolstered by this discovery, I spent a few days getting the whole Orange Pi decoder display pipeline working in vanilla. This too required a patched version of FFmpeg, but even once I got in the video to decode, I still couldn't get it to show on the screen. Instead, I just get this cryptic error message. Well, it turns out the Orange Pi's GPU requires texture widths to be evenly divisible by 64. For most common video sizes, this isn't a problem, but for the Wii U, it is. Not to worry though, it's perfectly fine to just pad the video width out and then only draw this part of the frame. But of course, if we do that on the CPU, that'll waste a lot of valuable time and CPU cycles. Remember, the whole point of this is no latency. What we'd really want is for the decoder to add this padding itself before sending it over to the GPU, but is it even capable of doing this? Well, yeah, it already does. In fact, it pads them out to ensure they are divisible by 16. Yeah, once again, it's like nobody actually thinks these decoding pipelines through. So if you're unlucky enough that rounding your video width up to the nearest 16 is not the same as rounding it up to the nearest 64, you're screwed. Cryptic error. Thankfully, this ended up being fairly simple to solve. The decoder's alignment can be configured. Not through any basic setting though, you have to edit the Linux driver's source code. A little annoying, but really no big deal. But the effort paid off, because what we have here is pretty much a latency-free gamepad clone. Okay, well, to be completely transparent, it's not literally zero latency, but what it is effectively on par with the original gamepad, which, you know, is the whole point, and probably about as good as we can hope for. Not to mention, the Orange Pi Zero is actually considerably more powerful than the Raspberry Pi Zero, and I'm yet to notice any significant lag spots. It's ironic that the main reason I was attracted to the Orange Pi Zero, the 5 GHz Wi-Fi, ended up not working out. But a completely unadvertised feature, the zero latency decoder, put it head and shoulders above the competition. So if you're going to build a whole new gamepad from scratch, this seems to be your best bet, at least at the moment. And no, I haven't been paid to say that, this is just what I found after a lot of trial and error. The only problem is, you might actually have a hard time finding one. While I was lucky enough to buy mine 2 years ago when you could get a baseline 2W for only $13, the current RAM crisis has made them explode in price, with some listed as high as $150. And there's an elephant in the room here. Yeah, it's cool to see a whole gamepad run on something this small, but it's not a whole gamepad, is it? We still need a screen, speakers, a microphone, motion sensors, a webcam, hell, even the case has to come from somewhere. Sure, it'd be fun to build, and you might even be able to make something a little nicer than the gamepad considering the advancements in screen and battery tech since then. But it's not exactly a practical option for the vast majority of people. Not to mention, we're talking at least $100 worth of parts on top of whatever Pi you use, so you're not really saving money over buying a secondhand gamepad either. I have to wonder if this is also why Nintendo's early plans to allow multiple gamepads ended up falling through. I mean, how could they justify asking families to spend over $100 each for a second, third, or even fourth gamepad? I can see why they might have felt sheepish about doing that. So while all of this Pi stuff has been fun and cool, if we want a gamepad replacement that works for the average person, we'll have to come up with something a little smarter. Hey, thanks so much for watching. I hope you enjoyed this installment of the Wii U Gamepad clone, and sorry it's all taking so long. This has been an incredibly complicated project, and we haven't even covered half of it yet in these videos. And honestly, the only reason I've been able to do as much as I have has been thanks to my patrons and YouTube members, the people scrolling on the screen right now, who I am incredibly grateful for. You know, the nature of my videos means I can't upload that frequently, so my ad revenue is usually not that great. Sponsors help when I can get them, but that's become increasingly rare. Maybe because of my inconsistent schedule, or maybe because sponsors don't want to be aligned with console moddings and decompilations, or maybe because you guys are really smart and already know how to get VPNs and set up websites. So your support really is what makes the difference here. I love what I do, and I'm incredibly lucky that you guys enjoy it too, but it is a lot of work for one person. I'd love to one day be able to hire someone on to not only help get videos out a lot faster, but also allow me to focus on the really important stuff rather than all of the minutiae all the time. If you like what I do and want to help me with that goal, consider joining. In addition to supporting for only $2 a month, you'll get at least one monthly bonus video, usually something casual where I just talk about recent progress I've made. And of course, you'll get to see main channel videos well before everyone else. Anyways, thanks again for all of your support, I really do appreciate it. I'll see you all in the next one. Bye guys.